Record video. Okay. All right. Chapter 18. First, on Monday we already learned the one reaction kind of addition of a hydride. Okay. So for additional hydride case, we have the first one. Okay. So if you start with kind of the aldehyde. Okay. Right. After addition of the hydride. Okay. So you generate kind of the primary alcohol. Okay. Yeah, just kind of a primary OH I label like this way. Okay. And if you start with kind of the ketone, okay, right. And after reactions, okay, you generate kind of a secondary alcohol, okay. Which, okay, yeah, that's something keep in mind, okay. All right, so we continue learn some kind of the new nucleophilic addition reaction to carbonyl compound, okay. Yeah, if you have any question, just type in the chart window, okay. Okay, the second reaction we're gonna learn is kind of addition of the hydrogen cyanide, okay. And for this reaction, actually kind of not hard, okay. So pretty much again you have kind of aldehyde ketone. I draw aldehyde ketone like this way, okay, and then react with the hydrogen cyanide, okay, HCl, okay. Right. So the real nucleophile kind of CN and the hydrogen kind of will pick up by the oxygen, okay. Right. And then after reaction, okay, so generally something like this, okay. CN, okay. CN attack kind of the carbonyl carbon, oxygen pick up hydrogen, okay. And this guy we call kind of cyanohydrin, okay. Yeah. So remember, we learned kind of in the previous chapter, actually kind of the 2 chapters ago, okay. So chapter 11, halohydrin, okay. Halohydrin kind of we did kind of mechanism 2, okay, for the addition reactions, okay. Bromination, chlorination in kind of aqueous solutions, okay. Halohydrin, okay. So the hydrogen, I guess, probably means kind of OH group, okay, and then halo means kind of chloro-bromo here, okay. Here kind of we have kind of cyano group, okay. That's why it's called kind of cyanohydrin, okay. And for the mechanism, actually kind of pretty straightforward, okay. So just what happened, kind of the hydrogen cyanide is kind of weak acid, okay. So generally some kind of cyanide kind of the anion, okay. So attack kind of carbonyl carbon, okay, and then open the CO double, okay, and then you generate something like this, okay. Right. And then falling kind of there are some kind of release the hydrogen case. Oh yeah, if you like just kind of draw the on the kind of screen, okay. So either way is fine, okay. And then let's give kind of final product, okay. Pretty straightforward, okay. And for this reaction, okay, so just some of you already noticed, okay, when I draw this kind of arrow, okay, so it shows kind of the equilibrium kind of arrow, okay, so double head, okay. But the one going forward one kind of the pretty long one, and go backward one kind of pretty short one, okay. The reason for that kind of this reaction actually kind of reversible reaction, okay. So that's here. So this reaction kind of reversible, okay. Okay, but with very high equilibrium constant, okay. So the prefer goes kind of product directions, okay. And so you can see here, okay. So the regular ketone react with hydrogen cyanide, okay. So the K equilibrium constant kind of the 32. That's pretty much I would say kind of 90% kind of the product kind of generated, okay. So so that's different from kind of the reaction 1, okay. So reaction 1, okay. So that's the hydride kind of the very strong nucleophile, okay, irreversible, okay. So and they see the cyanohydrin reactions, okay. So reversible, but here the high equilibrium, okay. So you can keep in mind, okay. And if we are if there are kind of a benzene ring, okay, conjugated with kind of a carbonyl compound, okay, so like a ketone aldehyde, okay, so that's here the equilibrium kind of goes kind of much kind of balanced, okay, and a much lower kind of binding kind of equilibrium kind of constant. Okay, the reason for that kind of we learned in the previous chapter. Okay, so the positive charge can delocalize in kind of the benzene ring. Okay, and then make this carbon less likely attacked by nucleophile. Okay, and but once you this carbon attacked by nucleophile. Okay, like hydrogen cyanide. Okay, then break up the conjugation. Okay, so that's not preferred. Okay, so those resistances resonance kind of stabilizations. Okay, so that's why the kind of the equilibrium constant kind of much lower. Okay. All right. Okay. So that's the second reactions. Okay, second hydrogen reactions. Okay. So now we move to the probably most important reaction for this chapter is kind of addition of the carbon carbon nucleophile. Okay. And for this the reactions kind of I will say kind of also most famous reactions. Okay, most famous reactions. Okay. So addition of the carbon nucleophiles. Okay, so we will learn two reactions. Okay, under the carbon nucleophile. Okay, one is kind of called Grignard reactions. Okay, so that's we list here. Okay. Yeah, Grignard reaction kind of as I said, kind of maybe the one of the most famous organic reactions. Okay, and there's one story. Okay, so my dentist. Okay, so one day told me I told him kind of I'm the organic teacher. Okay, so organic chemistry teacher. Okay, and he said, oh, when I was kind of the grad student, undergrad student. Okay, so I learned kind of organic chemistry. It's hard one. I still remember kind of Grignard reactions. Okay, but all other kind of reaction I totally forgot. Okay, so that's the pretty kind of pretty famous kind of reactions. Okay. So for Grignard reactions, okay, so you need kind of the carbon nucleophile. Carbon nucleophile, okay, so means kind of carbon has kind of relative negative charge species. Okay, relative negative charge species, okay, we kind of we call it carbanion. Okay, carbanion. Okay. And so the most efficient way to generate kind of the carbanion is kind of this carbon can attach with kind of the metal. Okay, metal, normally speaking, kind of has a very low electronegativity. Okay, so in this case, once the metal dissociates, okay, so the carbon will gain kind of both electrons, okay, become kind of negative charge species. Okay, right. But for the carbanion, okay, so that's very unstable. Okay, it's kind of very strong base and also a strong nucleophile. Probably the most strongest kind of base we learned so far. Strong base. Okay, so can react with any polarized kind of hydrogens. Okay, so like water, alcohol, amine, capsic acid. Okay, so that's one thing keep in mind. Okay. And for the Grignard reactions, okay, so we'll learn two organometallic compound. Okay. One is called kind of Grignard reagent, another called kind of the organolithium reagent. Okay, so depend kind of what's the metal. Okay, right. For the Grignard reagent. Okay, so so here this reaction actually kind of the Grignard reaction kind of the totally take like 3 steps. Okay, the first step we have to prepare the organometallic reagent. Okay, so either Grignard reagent or kind of lithium reagent. Okay. So for Grignard reagent, okay, preparation, okay, so at least here, okay. Okay, so actually kind of pretty straightforward. Okay, so you have some kind of the alkyl okay, normally kind of chloride, bromide, okay, and directly react with kind of the magnesium kind of metal, okay. And then so somehow kind of magnesium kind of metal insert between kind of alkyl group and also the alkyl halide. Okay. And then you generate kind of Grignard reagent. Okay, so that's the Grignard the reagent kind of the regular kind of structure. Okay, so because the magnesium has kind of the low electronegativity, it has kind of partial kind of positive charge, and then this the alkyl group will have kind of partial positive negative charge. Okay, so that's we generate kind of the organometallic kind of the reagent. Okay, and so similar situations kind of for the lithium reagent. Okay. So lithium reagent kind of we start with kind of still aqueous halide, okay. All right, so this time, we react with kind of the 2 equivalent of lithium, okay. So lithium metal, okay. All right, so after reaction, okay, different from kind of magnesium because it has kind of 2 valence kind of it's kind of 2, okay. So in this case, has kind of 2 attachment, okay. But for lithium reagent, okay, so it only has kind of 1 attachment, okay. And then another lithium kind of pick up the hydrogens, okay. Just kind of lithium the halide, okay. And again, kind of partial negative charge, possible positive charge, okay. All right. And here's kind of some examples, okay. So the first one is methyl iodide, okay, reacting magnesium, okay, and then you kind of methyl magnesium kind of iodide, okay. And second one kind of even you don't need to be kind of aqueous group, okay, you can kind of aryl group, okay, can do this reaction, okay. It's kind of bromobenzene, okay, so react with kind of magnesium, okay, and then just kind of phenyl magnesium kind of bromide, okay. And then last one kind of just prepare organolithium reagent, okay. So we use kind of lithium and with bromo benzene, okay. And for this reaction, okay, so normally speaking, kind of the most common solvent kind of either you can use ether, okay. Or kind of THF, okay. So THF kind of we can call kind of cyclic ether, okay. 5 membrane, okay, there's kind of oxygen, okay. So the reason why we have kind of ether is kind of hard to stabilize kind of the center magnesium, okay. So the 2 ether reagent kind of coordinate is kind of magnesium how to stabilize, okay. And so next week, okay, so lab will learn kind of how to use Grignard reaction prepare kind of capsaicin, okay. So use this kind of magic, okay. So you add some kind of the green magnesium kind of metal into the halide kind of the solutions, okay. So gradually kind of the magnesium kind of gone, okay. Kind of the metal is gone, okay. And then you turn kind of little bit mixtures, okay, and also little bit thick solutions, okay. And just keep in mind, okay, the Grignard reaction kind of very sensitive to water, okay. So both Grignard reagent and also the lithium reagent, okay. So very strong basically react with any acidic kind of hydrates, okay. So tiny amount of water will kill your Grignard reagent, okay. So that's the one example, okay. So they see the lithium reagent as kind of the example, okay. So quickly pick up the 1 proton acid base reaction pretty much, okay. And then just kind of not anymore kind of lithium reagent, okay. So in other words, okay, must keep kind of water and also the alcohol out of all your whole systems, okay. So so that means kind of next week lab, okay. So you guys kind of make sure absolutely no water, okay. And so this Grignard reagent kind of even too reactive, okay. So you cannot have any kind of the functional group can react with the strong base and also a strong nucleophile, okay. Here are some kind of examples, okay. All right. So if you have some kind of alcohol in the kind of your functional group or kind of in your actually reaction system, okay. So the Grignard reaction, Grignard reagent will react with it, okay. So that's kind of acid-base reactions, okay. And if you have kind of ketone aldehyde in your reaction systems, okay, so Grignard reagent also react basically. So that's we just learn now, okay. So Grignard reagent kind of the strong nucleophile will do kind of the nucleophilic addition reaction to the carbonyl, okay. And if you have some kind of leaving group, okay, so like this kind of the aqueous halide, okay, right, and then the Grignard reagent can also react basically. So this time kind of work as kind of base, okay, you do kind of E2 elimination, okay, pick up beta hydrogen and kick out the link group with kind of double bond here, okay. And last one kind of you have some kind of the epoxide, we can open the kind of use nucleophile, okay. So either basic condition or kind of acid conditions, okay. But if you have kind of Grignard reagent in the system, okay, so that you will have kind of the reaction with kind of epoxide open the ring, okay. So pretty kind of reactive kind of reagent, okay, Grignard reagent, okay. All right, so that's the first step, okay. So prepare the Grignard reagent, okay, and then we move to the second step, okay. So that's actually kind of the real kind of addition reactions, okay. All right, Here just show you guys kind of the mechanism. Okay. So we start with kind of still the aldehyde ketone. Okay. So Grignard reagent. Okay. So what happened kind of Okay. So this whole part. Okay. So AQ group bring this shared electrons all goes to kind of this carbon. Okay. All goes here. Okay. And then open kind of CO double bond at the same time. Okay. If you want to add on pairs, that's fine. Okay. Okay. And so that's the second step. Okay. And then we will learn kind of the third step and the second step together. Okay. The third step kind of we call kind of the workup. Okay. Okay. So that's not done yet. Okay, because you have kind of the negative charge actually kind of what happened kind of the magnesium actually kind of here. Okay. So generally kind of somehow kind of salt. Okay. Right, and then the third step, okay, so you do some kind of workup, okay, so you apply some kind of acid, okay, it's H plus, okay, so this kind of O minus will pick up here this acid, okay, and then give you kind of a final alcohol, okay, and then for the magnesium part, kind of become kind of we'll do workup, okay, so MgOHX, okay, so most time become this one, but here normally speaking, you don't need to draw kind of the inorganic part in the organic reactions, okay. All right, so after this, okay, you can see kind of for the Grignard reaction, actually we generate kind of alcohol, okay. Okay, alcohol, okay. So pretty much you add one alkyl group onto kind of carbonyl-carbon, and also the oxygen on carbonyl-carbon, okay, so the oxygen on kind of carbonyl group, okay, so pick up hydrogens, okay, generate kind of alcohol, okay. And so really depends what's of the starting material, okay, so we can generate kind of different alcohol, okay. So that's here. Just a little bit comparative with kind of first kind of the hydride addition, okay. So hydride addition, okay. So if we start with kind of the aldehyde, okay. So then kind of primary alcohol, okay. But for Grignard reaction, okay. So if you start with aldehyde, okay. Okay, I just ignored kind of workup stage, okay. Actually, you generate kind of secondary alcohol, okay. The reason for that kind of you need to put one more R group onto kind of the RQ group, okay. So carbonyl carbons, okay. So that's your general kind of secondary, okay. So if you start with kind of ketone, okay. Yeah, someone ask questions, okay. Is this the workup stage right here? I just there should be kind of workup stage, okay, but I ignore it, okay, okay. Just kind of don't want you guys kind of get too many information here, okay. So suppose the old Grignard reagent, okay, so Grignard reaction you should have kind of workup stage, okay. Yeah. All right, okay. So we continue, okay. Ketone, okay. So for ketone, actually you generate kind of the tertiary alcohol, okay. Yeah, see the difference? Okay, so here, okay, so if you do the hydride addition, okay, so ketone generate kind of secondary alcohol, okay. Right, and then someone asked kind of can we prepare kind of primary alcohol by Grignard reaction? The answer is yes, okay. So this time, okay, so that's right, okay. Work up just kind of O minus pick up the hydrogen, okay, pick up hydrogen, eventually give alcohol, okay. So all right, so if we start with kind of the formaldehyde, okay. Right, so that's the two hydrogen attached to the center carbonyl group. Right, and then we do the similar reactions, okay, and then we generate kind of primary alcohol, okay. Okay, so this H2 from kind of original kind of the aldehyde, okay, so that's primary alcohol. Okay, so that's something please keep in mind. Okay, so how do you prepare alcohol, and then what kind of alcohol do you need? Okay, all right. Someone asked about kind of okay, so actually kind of let's first give you guys kind of one example. Okay, Grignard reactions. Okay, so for the Grignard reaction kind of exam quiz. Okay, so sometimes kind of ask you kind of draw from scratch. Okay, so from Ylides, and then how do you generate kind of the Grignard reagent? Okay, how do you kind of do the addition reactions? Okay, and then how to do the workup? Okay, but sometimes kind of maybe already provide you the Grignard reagent. Okay, so that's you can start kind of from second step. Okay, all right, and then, all right, here I use formaldehyde. Okay. And then also I will list kind of workup. Okay, so workup kind of the H plus. Okay, all right. Okay, so the whole thing. Okay, so once the reaction is done. Okay, so maybe. So from here. Okay, so from now on probably I use more kind of colored kind of pen. Okay, show the different component. Okay, so where's kind of the different kind of the region kind of come from. Okay, otherwise the easily get confused. Okay, all right. Okay, so the for Grignard reagent can only contribute kind of AQ part, okay, this part, okay. Right. And then for the alcohol, okay, actually from kind of the aldehyde, and then when you do the workup, okay. Yeah, so that's the final product, okay. Okay, and then one important thing kind of if you tertiary alcohol, okay, is a product, okay. When you do the workup, okay, so you have to use the weak acid, okay, pretty weak acid, okay. Most common kind of the weak acid for the Grignard reaction workup is kind of ammonium kind of chloride, okay. So why we cannot use strong acid, okay? So just show you guys kind of one example, okay. All right, so we use ketone, okay, ketone gives some tertiary alcohol, okay. And then here I also instead of use Grignard reagent, okay, so I use the lithium reagent, okay. Yeah. So for sometimes kind of the exam quiz, okay, so some question, okay, so we no start from kind of the first step, we start kind of from second step, already provide kind of lithium reagent and also Grignard reagent, okay, so it doesn't matter, okay, so maybe still show you guys kind of a different color, okay. Right. So this part, okay, from your lithium region, okay, so count carbon numbers, okay, you have 1, 2, 3, 1, 2, 3, okay, so a new bond actually kind of here, okay. That's the new bond positions, okay. Right. Okay, and so for the tertiary alcohol, okay, like I said, okay, so normally we use the kind of weak acid, okay, ammonium chloride, okay, so that the O minus will pick up only one hydrogen, okay, give kind of the final alcohol, okay. Right. But if you use strong acid, okay, so strong acid, okay, so what happened kind of even reaction will generally give kind of the major product, okay. So for example, okay, so here we use kind of the HCl, okay. Right. So if you use HCl, okay, so won't stop at kind of pick up only one hydrogen, okay. So won't stop at kind of alcohol stage, okay. Quickly, this OH group will pick up another proton from kind of strong acid, okay. You generate kind of water at the link group, okay. All right. So water is kind of pretty good link group, okay, and easy kick off, okay, and also because it's kind of tertiary alcohol, tertiary kind of alcohol, okay. So just kind of tertiary carbon cation, okay. Tertiary carbon cation, okay. So it's pretty stable, okay. And then you can have kind of E1 emission, okay, some kind of the base, okay, maybe some water can pick up these protons, okay, and eventually you generate something like this, okay. Yeah, that's not ideal product, okay. Okay. So that means kind of if you form kind of the tertiary alcohol, okay, so be careful, okay, so use weak acid, okay, so ammonium chloride, okay. All right, and for this reaction, okay, so one important application is kind of prepare some kind of capsic acid case from kind of the Grignard reagent case. So that's actually kind of pretty useful kind of application, okay. All right, so the mechanism already show there. Okay, I just show you guys kind of the general reactions. Okay, so we have kind of the Grignard reagent. Okay, and then react with kind of carbon dioxide. Okay, all right, and then after reactions, okay, you generate kind of the carboxylic ion. Okay, CO minus. Okay. Right, and then you do the workup, okay. Yeah, still some kind of acid, kind of even some of the weak acid, okay. And then you generate kind of capsic acid, okay. Okay, so the mechanism kind of show there, okay. So still this organometallic kind of the R minus, okay, attack kind of the oxygen kind of in the carbon dioxide. Open kind of the CO1 or CO double bond, okay, and then you do the acid workup, okay, and that's actually kind of our next week lab, okay, okay. So you have kind of a lot of fun, okay. So the carbon dioxide actually we generate kind of from the dry ice, okay. So you waste some kind of dry ice, okay, and then actually kind of for next week lab, we will kind of experience all three steps, okay. So you first need to make some kind of the Grignard reagent, okay. And then second kind of you add carbon dioxide actually dry ice, okay. You generate kind of a carboxylic kind of ion, okay. And then eventually you quench reaction, okay, add some acid, okay, and then give kind of capsic acid, okay. So that's the next week lab, okay. And here's kind of some kind of one example, okay. So we use kind of bromo kind of the naphthalene, okay. So convert kind of it to kind of its corresponding the capsic acid, okay. And one thing I just forgot to mention, okay, for the Grignard reactions, okay. So because the organometallic reagent kind of the very strong kind of nucleophile, okay, and then this one actually kind of irreversible, okay. Yeah, irreversible, okay. So you can see kind of when I draw the kind of mechanism or whatever kind of I just draw kind of straight line, okay, because this reaction kind of just once you push it forward, okay, cannot go back to kind of already have kind of ketone, okay. And again, okay, so make sure all your glassware kind of clean and dry, okay, no water, okay. So the water will easily kill the kind of Grignard reagent, okay. So in the lab next week, okay. So I'll talk about more kind of about next week lab, okay. So later, okay. All right. And like I said, kind of why the Grignard reagent kind of Grignard reaction kind of so famous, okay, because it's kind of very useful, okay. So to build up kind of very complicated molecule, okay. So from kind of a very simple kind of the aldehyde ketone, okay, and you can add kind of the alkyl group or kind of aryl group on the kind of the center carbonyl carbons, okay, and you can generate kind of very big carbon framework, okay. So example showed here, okay. So as you kind of make this tertiary alcohol from kind of based on kind of Grignard reaction, okay. So for this kind of types question, okay. So the first thing you need to do is kind of quickly identify what's the original kind of carbonyl carbon, okay. So this blue one's kind of original carbonyl carbon, okay. So that's the with OH group attached, okay. The original one, okay. Right, and then you have to kind of think about kind of how do we break it up, okay. So for this on symmetrical kind of tertiary alcohol, okay. So you can break up in three ways, okay. So either ways, okay. Right, so we can this the phenol part from Grignard reagent, okay, and then attack this we call kind of two butanone, okay. Oh the methyl group, okay, are from Grignard reagent, okay, and attack this the ketone, okay, and then all kind of this methyl group, okay, from Grignard reagent, okay, attack kind of the keto with kind of phenyl and the methyl group on, okay. Yeah, so that's the either way, any of these three mechanism kind of working, okay. All right, so that's about kind of Grignard reactions, okay. So now we move to the next reactions, kind of that's probably fourth one, okay. Called the Wittig reactions, okay. So yeah. Yeah, so the reaction we learned today is kind of the all very famous and also very kind of important, okay. Wittig reaction, okay. So this reaction also use the carbon nucleophile, okay, as the carbon anion as kind of the nucleophile, okay. And but the kind of different kind of the carbon nucleophile, okay. So this time the real carbon nucleophile is kind of called the Ylides, okay. So Ylides, okay, Ylides, okay. And so for this reaction, okay, so it's also irreversible, okay. Keep in mind, okay. Yeah, because we still use kind of very strong nucleophile, okay. And the general reaction actually kind of pretty straightforward, okay. So there's one showed on the screen, okay, and I will show you another version, okay. So you start with kind of aldehyde ketone, okay. So we still draw like this way for the aldehyde ketone, okay, and then Ylides, okay. So there's one showed on the screen, okay. So I will show another way to draw the Ylides reaction, Ylides region, okay. So this is kind of 3 phenyl group, okay. So and then should kind of phosphorus, okay, triphenylphosphine, okay. This is the P, okay, phosphorus, okay. R1, R2, okay. So actually that's the kind of same thing as I drew kind of on the screen, okay. So on the PPT file, okay, because when you do kind of resonance, okay. So the electron shift to kind of carbon, okay. Right, and then actually kind of this should be negative charge, kind of. Carbon is negative, and then phosphorus is kind of positive, okay. So that's the another way draw kind of Ylides region, okay. So this the whole species we call kind of Ylides, okay. Okay. Right, so this Ylides region, okay, will react with kind of carbonyl group, okay, and then the final product you generate kind of the alkene, okay, CC double bond, okay. Right, so the new bond I kind of draw it in the blue, okay, drawing kind of in green, okay, and then okay. Right, you see kind of for the alkene, okay. So part of the CC double bond, okay, are from kind of original the carbonyl carbon, the aldehyde ketone, okay. Another part actually from kind of Ylides, okay. And then there's another product, okay. So okay, called kind of triphenylphosphine oxide, okay. Right. So if you take a second look of this reaction, okay, you find kind of pretty interesting, okay. So looks like the some kind of exchange happened, okay. This some exchange, okay. So for the aldehyde ketone give out kind of oxygen, okay, and then get the carbon part from kind of Ylides region, okay. Right. Go here, okay. And then for the Ylides, okay, so give out kind of this carbon part, but the gain oxygen, okay, gain oxygen, and then oxygen attached kind of phosphorus, okay. So that's the one way you learn kind of the Wittig reaction, okay, it's symbol kind of exchange, okay. So you change kind of a component, okay. So that will make your life much easier, okay. Right. So for the Ylides region, kind of the pretty unique one, okay. So there's some people maybe already has a little bit idea. Okay, so for the phosphorus, okay, has higher electronegativity compared with carbon. Okay, suppose phosphorus has kind of negative charge and then carbon has kind of positive charge. Okay, but for this one kind of reversed. Okay, so the kind of reason for that kind of phosphorus has kind of the trifon three benzene ring attached. Okay, and then easy to kind of the stabilize kind of positive charge. Okay. And then that's why kind of carbon easily pick up kind of the negative charge. Okay, so the Ylides kind of actually kind of a very unique kind of species. Okay, you have kind of opposite kind of charges. Locations. Okay, for the kind of atoms. Okay, so this species actually full name is called kind of the phosphor Ylides. Okay, so if you move kind of higher advanced organic synthesis, okay, there are kind of all kinds of sulfur Ylides. Okay. Psyllium kind of the Ylides all kinds of that's the long story case. So for the Ylides case, so because they are kind of resident structure. Okay, so that's why this species kind of the relative stable. Okay, but normally speaking, kind of similar like the Grignard reagent. Okay, so the people prepare Ylides reagent kind of at real time. Okay, so it's kind of only purchased. Okay, because this one still work strong base strong and I would say kind of strong base strong nucleophile. Okay, so easy to react with any reagent. Okay, right. So in this case for the Wittig reaction. Okay, so actually kind of also maybe get a new page. Okay, actually also the has only two steps. Okay, no workup. For Wittig reaction. Okay, so the first step kind of you need to prepare the Ylides. Okay. Ylides reagent. Okay. All right, and then for the reaction to prepare the Ylides reagent. Okay, I just draw you guys kind of the general reactions. Okay, actually kind of two-step reactions. Okay. All right, should be kind of H. Okay, only one hydrogen. Okay. Right. Okay, so R1, R2 can be kind of also the hydrogen. Okay, so let's keep in mind R1, R2. Okay, so that's you start with kind of the triphonophosphine. Okay, react with kind of any actually kind of I would say kind of primary, secondary, and only primary, secondary, and also the methyl kind of active halide. Okay, so why not kind of tertiary? I will explain it soon. Okay. Okay, this reaction actually we learned kind of in before. Okay, so this is the very good nucleophile. Okay, attack kind of active halide. Okay, called the link group. Okay. All right, and then that's the general positive charge here, and then negative charge kind of here. Okay. And this reaction actually kind of we learned in the chapter 10. Okay, so remember I said kind of in chapter 10, phosphorus. Okay, as a nucleophile. Okay, so phosphorus and sulfur are very good nucleophile. Okay, in the phosphorus reactions. Okay, so I said kind of please remember these reactions. Okay, phosphorus attack kind of the active halide. Okay, so kind of this species. Okay, phosphorus kind of neutral nucleophile, good nucleophile, but weak base. Okay. All right, and then I ask you kind of try to remember this one because I will learn this one kind of in the later reaction. That's here. Okay, so Wittig reactions. Okay, but this species still not Wittig the reagent. Okay, so we have applied some kind of strong base. Okay, so most common strong base kind of the butyl lithium. Okay, so that kind of butyl group. Okay, and then kind of lithium. Okay, so very strong base. Okay. So this guy will pick up here kind of this proton. Okay. And then the arrow go back. Okay. So that's eventually give kind of a final Ylides reagent. Okay. Certainly you can shift a lone pair electron okay, between kind of phosphorus and kind of carbon. Okay. So that's the same thing. Okay. Right. So that's step one. Okay. Here, okay, just told you kind of the why the only kind of the primary, secondary kind of the aqueous halide can have kind of Ylides, okay, no tertiary, okay. So the reason for that, tertiary don't have kind of the hydrogen on the carbon, okay. So in this case, you cannot do the second step reaction. Okay? Second step, you take off the protons, okay, hydrogens, okay. So yeah, that means kind of the reaction stop at first step, okay. So no Ylides generated, okay. Yeah. All right. So that's something keep in mind, okay. Right, and then the second step is kind of the Wittig reactions, okay. Right. So for the second step, okay, so yeah, the mechanism kind of required, okay. So yeah, I will show you guys how to do it, okay. Right. Right. So we start with kind of Ylides reagent, okay. R2, okay. Make charge, okay. All right. And quite often, people hard time kind of to draw the Ylides kind of the mechanism, okay. So here I show you guys some kind of little bit small kind of skill, okay. So yeah, you put here the first Ylides region here, okay. And then second kind of you align kind of ketone aldehyde, okay. How do you align it, okay? So you put oxygen, okay, close to the phosphorus, okay, and then the carbon, okay, close to carbon, okay. Ylides carbon, okay. You do here, okay, like this, okay. So still here, okay. That's either aldehyde ketone, okay. So why you align like this way, okay? Because you're remembering the aldehyde ketone, okay. So oxygen has kind of partial negative charge, and carbon has kind of partial positive charge, okay. So the charge can match, okay. So negative like positive, positive like negative, okay. So you align like this, okay. All right, and then now we can draw the arrow, okay. Right. So these here the lone pair electrons on the Ylides, okay, will attack kind of the carbonyl carbon and then open the CO double bond, okay. Right. And then we generate some kind of intermediate, okay. You find kind of the no oxygen has the negative charge and the phosphorus has kind of positive charge, okay. And then the kind of the close the somehow kind of full membrane, okay. Right, something kind of this full membrane, okay. So carbon together, phosphorus pick up oxygen, okay. But yeah, that's not final product, okay. So you have the shift here the electrons, okay. So we will shift like this way, okay. So the oxygen carbon bond kind of break up, okay. And then these shared electrons all gets to kind of the phosphorus and also the oxygen, okay. And then the carbon phosphorus kind of bond break up, okay. And then give kind of the carbon, okay. So you shift electron like this, okay. Right. And then afterwards, okay, so you generate some kind of these two parts kind of totally break up, okay. So yeah, these two bonds, okay, break up, okay. Right. And then you generate kind of the final product, okay. So transphosphine oxide, okay, and then the arcane. Okay. So this part from original aldehyde ketone, this part from kind of Ylides reagent, okay. Right. So make sure kind of know how to draw the kind of mechanism, okay, from step one, okay. So Ylides preparation until here, okay. So like I said, kind of from this chapter, kind of mechanism kind of much more kind of complicated, okay. Make sure you know how to push electrons, okay. And actually for this reaction, kind of the first step actually kind of very similar to the reaction we learned so far. Okay, so like addition of hydride, addition of the cyanohydrin, okay, and also addition of the Grignard reagent. Okay, so but the only difference kind of happened on the second step. Okay, second step kind of we call kind of the elimination. Okay, so addition elimination. Okay, so that's the first reaction kind of we have to push one more step, addition elimination. Okay. All right, and so so just make sure you understand which part kind of reaction happened, okay. And here are some kind of example, okay. So we we have ketone react with the Ylides, okay, and then you just kind of alkene, okay. Try for the first thing you can draw it, okay. Or yeah, if you don't want to draw it, that's also fine, okay. All right. And so second one is kind of we start with kind of so that's the actual kind of part of the Ylides reagent, okay, and then react the butyllithium, pick up kind of protons, okay, pick up these protons, we generate kind of real kind of Ylides reagent, okay, and then react with kind of aldehyde, okay, and then put on here, okay. So yeah, so that means kind of sometimes kind of Ylides reagent already provided for you, okay, or sometimes kind of we just stop that here, okay. Or sometimes kind of start here, okay, or start here, okay. So we can have all kind of situations, okay. So we have to identify which stage the reaction already provided for you, okay. Okay, and then give you guys kind of more example, okay, more example, okay. So for the Ylides reagent, okay, so Ylides reaction, Wittig reactions, okay. So most important kind of you need to recognize kind of which part react, okay, and then what kind of product is generated, okay. So we start kind of easy one, okay, right. So that's the aldehyde, okay, and then this is kind of CH double bond, okay, with kind of the trifenophosphine, okay. So that's pretty easy, okay, right. So that means kind of remember, okay. So like I said, kind of Wittig reaction pretty much you just do some change, okay. Aldehyde ketone keep the carbon part, okay, and then you build up the new bond, okay. So if you have kind of a color pen, you can draw same thing as me, okay. All right, the CH2 from kind of the Ylides, okay, CH2 from Ylides, okay, and then that's the kind of you don't need to kind of another product, okay. And sometimes kind of reaction can get the more complicated, okay. So show you another example, okay. All right. So for this example, okay, Ylides, yeah, that's right, okay. Ylides or trifenophosphine, okay. Trifenophosphine, okay, not fate, okay. Fate has kind of oxygen on it, okay. Trifenophosphine, okay. Right. Second one actually kind of we start from scratch, okay. So from kind of the active halide, okay. And then we make a Ylides, okay, first step, and then try to react with kind of the ketone this time, okay. And probably show you guys kind of still color chalk, okay. Right. So the key thing kind of you have to recognize which part react with which part, okay. So the fourth thing, kick off the bromide, okay. Kick off this one, and then you generate double bond here, okay. Double bond here, okay. Right. So that's another phenyl group, okay. Right. Okay. So that's this carbon build a double bond with kind of the phosphorus, okay. All right. All right. And then falling kind of react with kind of ketone, okay. So again, okay, so you have to recognize kind of which part from kind of aldehyde ketone, which part from kind of trifenophosphine, okay, Ylides reagent, okay. All right, so pretty easy. Like I said, kind of do change, okay. So still kind of we generate an alkene, okay. Right. And then this part, okay, will become kind of part of the alkene, okay. Right. And then if you want to draw trifenophosphine oxide, okay, that's fine. Okay, if you don't want to draw it, that's no big deal, okay. So this part all same, okay. Difference here, okay. So all right, I guess that's it for today, okay. And so we continue kind of this chapter on Friday, okay. So talk about kind of the synthesis use of the Wittig reactions, okay. All right, do you guys have any questions?
Yeah, I have a question about the homework.
Oh, okay. All right. So if you have homework question or kind of lab report question, okay. So you stay on the keep your the Zoom open, okay. And then after I finish the lecture, okay, you guys can ask me, okay. Any question about the lecture today?